Let's start on this particular topic, that is federated learning, privacy preserving collaborative machine learning. We'll discuss about today. And I am Harsh Kashyap. I am pursuing postdoctoral. I'm working as a research associate at the Alan Turing Institute, London. I just finished my PhD from IIT Patna. And the agenda for this discussion will be uh, I'll put some trends that why everybody is knowing that why AI ML is important and how that AI ML has encroached to each of our lives. But how security breaches are happening, and why cyber security and machine learning should be clubbed together. And there is a need of privacy preserving machine learning. Every word is important in the topic: privacy preserving, collaborative, why collaborative, and machine learning. Then we will discuss about federated learning and the recent trends, and what are the still there is some issues, privacy issues in FL. There are many research papers which tells that is FL truly privacy preserving? Like FL was intended to be privacy preserving machine learning, but it is not exactly to be. So we will discuss those vulnerabilities, and then we will discuss some of the defenses or some of the mechanisms to fix that issue, and then we can have questions. So uh, everybody is aware about what AI is like, but at this particular time, what i- more than this slide I want to tell is that now the devices have become more intelligent than humans. Earlier we were teaching the devices to be intelligent, but now the devices are actually more intelligent than us. There was a AI safety summit in London this year, and industrialists from across the world like Elon Musk came and all. So they told that this is the first time that that there is something existing on this earth which is probably more smarter than humans, and those are the machines based on artificial intelligence. Like for everybody, we are surrounded by smart devices around us, and it is all AI that we are smelling, speaking, hearing, looking, writing, and all. Just for example of writing research papers, I can see now that there are a lot of tools that people are using. Specifically, you can see some research papers where a co-author is ChatGPT, and the big conferences are telling that you should not have an AI generated content in your research paper. In AI in India, obviously India is not behind anybody in this race. And currently there was a conference, and a professor from US, Professor Amit Seth, is a director of natural language processing. He visited India, and he told that there are multiple generation of AI. So in this generation, India should take it ahead, and the highlights of this, or the topics that India can pick are neurosymbolic AI and trustworthy AI. Like AI has developed, AI has covered a long way, but what we should pick now is trustworthy AI, private, secure AI, and AI which is safe. I will skip these slides. Uh, so, up, what ML and AI are basically built upon? They are built upon an extensive set of data, huge data set. Uh, so, does this data set comes? It doesn't originate from a single place, right? It originates from many of us. It originates. Everybody is generating data. Everybody who is using a smart device, an IoT device, or any device is generating a data. Even if we are watching YouTube videos, we are generating data. We are giving the patterns to somebody. If we are chatting with someone, we are generating data. We are telling that how the emotions change, how we write. Like it is obvious, if you type on your Google keyboard I am, then it will give you multiple suggestion. I am going to. So everybody is generating data, and that leads to data breach, which can be granularly seen as privacy breach or security breach, that are different. It can be classified into privacy breach and security breach. Both are different. When I tell privacy breach, it means a breach to an individual's privacy, personal and identifiable information, PII. When we say security breach, which has been studied since long, because that relies on the basic security parameters, CIA, confidentiality, integrity, and availability. So there has been seen multiple data breaches. Even in, the biggest companies like Apple, Meta, Samsung, they all have been impacted by this. So what are the challenges that every company wants to invest on data security? I will add here privacy. If you are not sharing or collaborating, then what challenge comes? You have a lower quality of data. You will end up with a volume of not reliable data, and there is a new concept now, synthetic data, that these buzzwords can be means I will motivate the students to note these words, like these are in the market now, and you can think and study a lot about this. Like synthetic data in itself is a big research term now. Like we don't want to give our private data, nobody wants to share their private data. Then how the organizations will develop intelligent models so they can use synthetic data? But is synthetic data also private is another question. There are many compliance issues. For example, in Europe it is called GDPR. In US there is something called HIPAA. Even in India, I cannot recall it now, there is a privacy bill now, DPPB. I could not spell it correctly. So there is a privacy bill even in India now, which doesn't allow the organizations to collect the data as it is from our smart devices. And then the next challenge is learning in silos. Silos means learning independently. Suppose that, for example, there are multiple banks in a country, and they all face some fraudulent activities. It may be anti-money laundering, for example. So while designing this, while designing a software, or while designing a machine learning software to be specific to combat those fraudulent activities, a bank cannot see all the possible cases. It is not possible for an organization to visualize all the cases, right? You can visualize, or you can have the data what you have faced, but multiple banks face multiple issues, right? But until they collaborate, everybody cannot have the complete information, right? So if you are learning in silos, uh, the players involved will make independent decisions, and you cannot have like the complete knowledge. But they don't want to share due to the market competition, or due to the privacy or security issues, whatever. Okay, so what is the need of the hour is secure learning with data generated from numerous connected devices. So the need is collaboration. Like we want collaboration, we want data sharing, but at the same time we want privacy and security to be ensured. So that's why federated learning is a quite promising solution. I will not say it is a solution to everything, but it can be thought mm, to, uh, to be uh, to be a solution which can be integrated with another privacy enhancing technologies, the pure cryptographic technologies, or some statistical measures to ensure privacy and security and collaboration, everything. It has a long history. Like before federated learning, fog computing was introduced by Cisco in 2015, and in 2016 federated learning came. Prior to that, it's simple that if you are learning in silo you cannot do more, but if you are learning together you can do much. So bring the data together. Small enterprises or even individuals are generating huge data, as we discussed. So it is really challenging to take advantage of this data. Um, so it requires manual intervention with data. But if you are giving data to a central authority, like if everybody is sharing the data to a central server for training, that will lead to a single point of failure. It will have a privacy and security, which even if you are sending encrypted data and all, it can be manipulated in between and all. These are some stats. Like there were expected to be 43 billion IoT connected devices by 2023. Okay, what are some issues when we talk about learning with smart devices? Like everybody have not only mobile phone, that you have a smartwatch and all other things which are generating data, but are they good for learning? So what are the constants that come? It comes some resource optimization, computation optimization, communication optimization. These are the major. Like when I say resource optimization, like our network is not reliable, our battery is not reliable, right? We suppose there's some processing is happening on the mobile, it is not guaranteed that the battery will be charged till that particular operation is completed. When we tell about computation and communication, though we can see that our mobile phones have 4 GB, 8 GB of RAM, but still they are not very well to train a large machine learning model, an LLM kind of thing on the mobile device, right? So it leads to computation challenge. And then there is a communication challenge, like you cannot transmit uh, like 10 GB of data every day, right, from your mobile. It will and everything is related. If you are doing so much of computation and communication, it will drain your resources of your edge devices, of your smart devices. And then there are some optimization issues, like what we will focus more going further on the security and privacy issues. So that comes from heterogeneous data, like a person in different state of India has a different, suppose that Google is training a keyboard learning, means text prediction model. So people in different states have different ways of typing, right? So the data is heterogeneous, so you cannot club all the data and learn it together. So it is called like learning from heterogeneous data. And then it raises some statistical challenges. Privacy and security will talk a lot about. And then the dynamic conditions and temporal isolations. So the question arises are how to collect data, like how to learn from data, how to secure the learning, how to ensure privacy, and how to audit the contribution. I think we discussed a lot about collect, learn, secure, privacy. Audit by means that, suppose for an healthcare machine learning setup, if big hospitals and medical stores are collaborating, then hospitals will have this problem that we are giving more data, we are giving more knowledge, but a medical store is not giving that knowledge, but receiving more knowledge. So one party is a big giver, but another is a big taker. So how to incentivize the giver and how to give the proper credit to everybody. There exist different computing architectures, like distributed computing is kind of an scaling. Here we don't talk about privacy and security much. That maybe security may be considered, but not from the perspective of privacy. It is about a scaling of the computation, on running the computation on different nodes. Maybe you are distributing your data, you are scaling your nodes. Decentralized computing, when we talk about decentralized computing, it means there is no central server, there is no single point of failure. So decentralized computing is something advancing from the distributed computing. Blockchain, like a much talked term, something, but still, according to me, it still faces a lot of computation communication challenges, and not at all. But the plus points of blockchain are that it clubs three things: security, that is not privacy. If I'm correct, it doesn't cares about privacy, it cares about security. It cares about P2P, like it is decentralized, and uh, it it has incentivization mechanism, that we tell that it has game theory concepts, it applies game theory concepts. So the problem that we discussed in the healthcare context, it has a solution for that, blockchain. Fog computing is just like, because we talked about the challenges associated with edge devices, because edge devices cannot do everything, cannot communicate directly to the central server. So they are introducing some middle layer fog devices and ensuring this, addressing the issues of computation and communication with the edge devices. Centralized learning, I don't know why I kept it here, it should be at the first. So it is the most traditional kind of learning, and then we will learn about federated learning in detail. It is like a 6 step process. Like in the first step, there is a server which trains a preliminary model. Suppose that multiple healthcare organizations want to train a model without sharing their data. Nobody wants to share their data. Then the central server will generate a model, a dummy model. It in the in the first step, the server will send that dummy model to all the edge devices. All the edge devices. In the second step, all the edge devices train that dummy model on their own local data. So now a model is trained. Data is not leaving the organization. Data is not leaving the premises of that particular organization or that edge device. Data is residing at that edge device itself. After the model training, not even the whole trained model is sent back because that will be a big chunk. Rather, they find the difference between that dummy model or the previous model and the new model that has been trained on that particular device, and that difference, that is called gradient update or local model update, or that is sent back to the server. Then the server receives those local model updates or gradient updates from multiple edge devices or multiple organizations, whatever, like uh, um, Federated. I will come that next, and then it aggregates all those gradient updates in the step 5 and sends back to the devices or organizations again. And this process goes in multiple iterations until like you are good with the good global model that has been learned. The federated learning is classified as cross silo and cross FL. Cross silo and cross FL federated learning. Sorry, cross silo and cross device federated learning. So when we say cross device federated learning, we tell FL is learning with multiple edge devices, multiple smart devices. When we tell cross silo, it means big organizations who have some computing powers, good uh, computing means they have resources. They are not resource constant. They are resource intensive. We already discussed about how federated learning works. Like this is the equation denotes the global model, how it is aggregated. So since we have received the global model update, we talked, right? The server received gradient update that you can see delta WTK. So that delta WTK is the gradient update of client K in iteration T, and all those gradient updates are aggregated and averaged. And because they are update, they are not the complete model, right? And since they were the difference to the previous global model which was sent from the server to the client, so they are added back to that dummy model or global model or previous model, whatever you say, and then the server gets the new global model. So by here we should realize that how federated learning restricted the data movement. It restricted the data movement, right? The data is in the premises, is with the individuals, is with the owner. The only movement is of something called model, and those who have taken the ML courses or those who visualize a model, how you visualize a model? A model is nothing but a matrix. You just visualize a matrix. Model is nothing but a matrix. Or let me tell you, uh, y equal to wx. You can write this equation, y equal to wx plus b, whatever. So here the model is w. If you write this equation, you can just visualize it. Y equal to wx plus b. Here w is a model which establishes a relation between x and y. X is your data. So for given data, what should be the y that I can predict? Sorry, for the given data x, what should be w, that is the model that we can predict y. So that w is the model. W is nothing but a matrix, a big matrix. It's not like simple image processing models have now billions of parameters. So if the LLMs, I think they have billions of, more than billions, many billion parameters. So this is what model, a machine learning model is, or a deep learning model is. So now rather than transmitting the data, you are transmitting a model. So when I talked here that the model is something, a matrix, even the data is something a matrix, but data is meaningful. Like you can directly see the data. Like if you encode a image data is nothing but some a matrix of some integers or some real numbers, right? But you can directly see that this is an image. If you will encode, decode it, or simply just put it into a format of image, you will see that it is an image, it is a text, right? But you cannot learn directly something from a model, because you must have learned in some courses data, information, and knowledge. So machine learning model is something kind of a knowledge. It's not directly the data, so you cannot directly infer the data, and that it aimed to do, that federated learning aimed to do, it aimed to preserve the privacy of the participants. So it is successful till here, but still the challenges. Have you ever used FL? Yeah, everybody of you are using FL, of us are using FL, because uh, we, whoever is using Android phone has Google Keyboard in it, and Google Keyboard uses federated learning. So when we get something like we are typing and we get the suggestions, it doesn't, from where the suggestions can come, it comes from, it learns from us. It doesn't comes somewhere from outside the world, it comes from us, it learns from us, from our typing strategy. We, a person in Bangalore will get a different next word prediction, a person in Patna will get a different next word prediction, a person in London will get different next word prediction. So obviously it is learning geographically, demographically, right? For a particular demographic it is learning. So how it is learning? And it is not possible that you have, as an individual, as a single participant, we have uh, created all those patterns. So it should learn from collaboration, right? It should learn collaboratively from multiple individuals. So how this is possible? And we don't want, right, do we want that whatever we are chatting with someone or whatever we are typing should be directly sent to a server? We don't want, right? So what Google claims to do is that Google sends a model to the mobile device. It trains on whatever we type in our mobile. The model is sent back to Google server, local server, not server in US, a local server there. Those are aggregated, sent back to our mobile device, and then we have this intelligent model which helps us in typing. However, there are many articles that how because we are not checking that how Google is coming inside our device and taking out what. So this is a different topic, and it has a lot of debate and all. But at this moment, let's visualize that, okay, what Google is claiming is that Google is coming, playing with the data, the model is playing with the data inside in the smart device, and what is getting out of the device is the model, not the data. Okay. Just an use case I will show. There are multiple hospitals, they are learning individually, so they have limited knowledge. Hospitals share their data with each other, they improve the knowledge, but they suffer privacy. So with federated learning, hospital shares a local trained model with a trusted server. Still, the server problem exists. A trusted server, that may be a single point of failure. The server aggregates and shares the updated global model back. And this is how FL works that. And it went in multiple iterations until the model is intelligent. There are multiple applications of FL now, both in terms of cross silo and cross device. When you say cross device, like Google Keyboard is a cross device application, but when big hospitals are collaborating, that is a cross silo application, cross silo FL. Even for web search, we have like Mozilla uses FL based prediction. Multiple hospitals here, like in UK, NHS Trust use FL for it. In medical, in finance, in traffic management, it has big applications, and the industries are adopting it. The big companies like Google, Apple, Microsoft, Samsung are using it for, I have made bold like for what they use, like text prediction. Google uses it, Apple used for privacy focused for Siri to improve voice recognition. Microsoft uses it for predictive text input. Samsung uses it for improving the on-device AI capabilities. Even in Asia Pacific, it is expected that FL market will reach $210 million by 2028. And what are the major verticals that it will be used in? That is finance, healthcare, life sciences, retail and e-commerce, energy and utilities, manufacturing, IT, telecommunication, automotive and transportation verticals. So these are the major verticals where FL will be adopted based on the prediction. Okay, in India also, like I think Geo works on a lot on FL. Bipro, TCS also have are talking about it. And yes, like where Indian companies invest, so we are investing a lot in IoT and AI. I don't know what investment means, to be honest. Like, uh, we more users of it, or are we more developers of it, is a different question. So now we'll talk about some challenges in FL, as you discussed that if the time is okay. Uh, I think if there is some question, we can, if any question arises from the previous slides, I'm fine to take it now. Otherwise, I will next I will talk about the issues or the challenges in FL.
Myself, Dr. Gokul, Dr. Kash,
Yeah,
I was like thinking about like in case if someone has to implement this federated learning, like what kind of
yeah.
infrastructure is required, like just for the sake of educational purposes.
I think for educational purposes, it can be even done on a single PC, because you have to simulate multiple devices, right? Like multiple devices are training models, local model. So it can be for a small like MNIST model. If you want to visualize FL with an MNIST model, or fashion MNIST model, or any machine learning model, it can be even simulated on a single device and visualized completely for, and obviously for training some large models like ResNet models, large image models, or large language models. Obviously we need GPUs, but like to visualize FL for academic purpose, we don't need some additional infrastructure other than the traditional machine learning deep learning models. To visualize it more well, what I can tell that like if someone wants to really visualize it, like this device is sending some model and some another device is sending some model, then also you need to set up a central device, a central server, and there we can run a server which is like a publisher subscriber mechanism, like I'm pushing and the server is listening. So that is also a traditional server. So nothing is new in FL. The only thing is new that data is not leaving this device. Data will be here itself, and that particular machine learning code will execute here. So but I will recommend, if any student wants to simulate FL, he can do it on a single PC itself. And I have those FL simulation codes also available on my GitHub, so I can share it with you. You can share it with one who want. Yeah.
Okay, thank you.
So can I proceed, Ed? Okay. So now we will talk about that. What are the challenges in FL? So it may be categorized as system and statistical. System challenges, we talked even this in context of edge devices, like constant resources, the device may be tampered, unreliable network, system heterogeneity. Statistical, like there are security and privacy concerns that will highlight, is FL fully private? Is FL fully privacy preserving? The answer is no. And why? And that we'll discuss. What are the major issues that can happen? So we visualized FL in terms that there are multiple clients, there are multiple participants and one server, right? So what client can suffer and what client can do? So client can suffer to inference attack. Inference attack is a reverse engineering attack on the model to learn about the data. Like like you are given W, right? Given W, y in y equal to wx, for a given W you want to learn x. Obviously it is difficult if you know neither x nor y. Sorry, if you don't know y, you want to know x, right? So it's difficult. You cannot like, that machine learning deep learning model is not as simple as y equal to wx. It is something like y equal to w square x square plus wq xq plus w to the power 10 in x plus, means it's very complex, right? So it's not very easy to visualize and reverse engineering. But yes, there has been many attacks proposed which are able to reverse engineer and learn that this particular model was trained on such data. So that is called inference attack on federated learning. It doesn't mean to be only on federated learning, it can be on simple machine learning also.
Harsh, you are muted. I think you are muted.
So your voice is muted.
Yeah, I don't know how I was muted. Okay.
Yeah.
So I was muted on this particular slide, right? Or from
Yeah, just only this slide.
okay. Okay. So uh okay. So when we talk about the attacks on federated learning, then just visualize that what attacks can be framed for a client or the participants, because in FL you visualize that there are multiple participants, there are multiple clients, and there is one server, right? So we learned that W is a model. In Y equal to WX, W is the model. Inference attacks means we want to learn X. For a given W, the attacker wants to learn X. For a given model, the attacker wants to learn on what type of data it was trained on. So that is called inference attack. By the way, inference attack is not only relevant to FL, it is also relevant to traditional machine learning or deep learning. Like Google released a model in the public, and an attacker can frame an inference attack to learn on what type of data it was trained. So that is called inference attack. It is not that straightforward, but yeah, to visualize, I am telling that given Y equal to WX, probably assume that you know Y, you know W, you, you can think that we can know X, right? But the model is very complex. It is something like Y equal to W square X square plus W to the power 10 into X. There are lots of variables and lots of the equation is too complex. That's why we call it a black box. We cannot visualize it mathematically. So, but still, doing some approximation, some statistical approximation, people are able to frame inference attacks that are also called a reconstruction attack on machine learning models or deep learning models to infer and learn that on what kind of data it was trained on. Poisoning attack. Poisoning attack means in inference attack, who could be the attacker? Like if many participants are participating, the attacker can be another client. Another client can be curious to learn from another client's model that is being transmitted. The server can be curious, who is receiving all the updates. He may be curious to frame the inference attack. So inference attack, if you are thinking in the concept of a threat model, like for students, specifically like this term you will come across in the research papers, threat model or adversary model. So it is a curious adversary model. It is called also called semi-honest model. Here everybody is executing their protocols honestly, but everybody is curious what other party has. So inference attack is simulated in semi-honest threat model. But what if the participants start behaving malicious? Like suppose there are 10 hospitals participating in a collaborative machine learning problem, but one hospital is not interested and he wants to he's malicious. One hospital is malicious, then that hospital can provide or transmit a malicious model to the server, and that will result in the whole aggregated model as malicious. This is known as poisoning attack. You are poisoning the model. You want to degrade, means a participant want to degrade the performance of the whole model, right? And it has been observed that only a single participant can poison the whole model, the whole aggregation, because just visualize like the data range, everybody is sending 1.5 to 1.2 1.9, just visualize, and one guy is sending 10. So it will pull the mean far from where it should have been. It should have been near 1.5 to 2, but now the mean is near 5. So a single participant can influence the global model aggregation, and that is called poisoning attack. That I'm more interested to be, and my research has been focused more on these inference and poisoning attacks. There are other attacks. Obviously, the server can be malicious. So the server can be biased. Like the server is receiving all the updates, right? Server is receiving updates from suppose 100 participants. Let's take Google. Like Google is receiving updates from all the states in India, but Google may be biased to one state and not aggregating the models received from that particular state. So that a server may be biased or lazy. The server may just ignore the updates from particular individual or the particular organization. And how the organization will know? The organization has because everybody is receiving the aggregated model back. So you don't know that whether this server has aggregated all the models or not. This problem has also been studied back in cloud server concept, where like we there is a question on that how we can ensure that cloud is giving back the correct result over what we desired. Like if like people store their data on cloud and they want some operation to be returned by the cloud, what is the guarantee that cloud is giving us back the correct result? Everything is fine. We make an agreement, we go into an agreement with the other party, but when we talk about the full trust, the overall because it has been observed that even after some SLA and all the agreements, the cloud server can give you the incorrect result and you cannot determine that the result was correct or incorrect. These are the traditional uh, attacks, the security attacks, like based on the confidentiality, integrity, and availability. And the every attack can be classified as active and passive attack. In active attack, the attacker is doing something extra. The attacker is malicious. In passive attack, attacker is just observing and doing the attack. Attacker is not doing anything other than the execution of the protocol. You can this cannot be directly related to the semi-honest and malicious threat model, but kind of relation is there. Then it depends on white box and black box attack. That how much access you got to the resources you want to attack. Like if you want to attack a global model, there are two type of access. One is called query only access. Means you can send some data and you can get a result, but you cannot see the model. You cannot see that matrix. That is called black box access or query only access. You can query the model. You can query a Google model and get the result, but you cannot see the Google model. So that is called black box attack, and you can just visualize that there are attacks proposed for black box access also. People have even attacked researchers. I'm not talking in terms of attackers. I don't know what attackers have done, and because they don't publish research papers, they would have attacked more. But even the researchers publish research papers with black box attack. Means they assume only query only access to a model, and they are able to reconstruct data and tell that on what kind of data it is trained on. To make a more clear visualization, I will tell you that there are inference attacks can be majorly classified into membership inference attack and property inference attack. So membership inference attack means the attacker wants to know that whether a particular individual or a particular sample was part of the data on which this model is trained on. And that is very sensitive, right? That is a very sensitive information to know from to know from the model. If you are able to infer such information from the model, it is very concerning. But there exist such attacks. These are called membership inference attacks. Another is called property inference attack, which is not that much concerning, but yes, it is. Like suppose a bank trained a model and an insurance company got the access to the model. Then the insurance company can learn from the model that okay, in this particular area, this much percent of people have income greater than this or less than this. This is called property inference attack. You are inferring a property from the model. However, the model was not expected to reveal the property. The model was only expected to reveal something else, that fraud or non-fraud. The bank model was only expected to that was a classification model between fraud and non-fraud. But the insurance company framed an inference attack over that model and is able to know that in in this particular area X% of people have this much income, and that is a leak, that is an attack. I think I don't think I'll be able to cover. There are lots. Um, in the coming next, there are lots of slides remaining, and these attacks are described in detail. So I would. What should I do? Should I take more slides, or should I directly jump to some? Is anything specific you want to uh, me to talk about, like some particular attack or defense? Could you please?
You can talk about different kind of attacks. What is the
Okay.
recent attacks?
Okay. So I will talk about the poisoning attacks. So the poisoning attacks can be classified as targeted poisoning attack and untargeted poisoning attack. In targeted poisoning attack, wants the attacker doesn't want to degrade the overall global model performance. The attacker is only interested in getting a particular type of samples to be misclassified. Like for example, take an MNIST classification model that everybody is aware of. That is an handwritten digit classification model that has 10 digits, 0 to 9. So the attacker is only interested in digit 9 to be misclassified at digit 6. The attacker is not interested in misclassifying all other digits. So this is called targeted poisoning attack, and that is majorly classified as label flipping attack and backdoor attack. Not majorly classified as, rather I will tell these are the attacks that are targeted poisoning attacks, label flipping attack and backdoor attack, and you can visualize it in broader picture. Like I will just give an example of these attacks, and we can visualize a broader picture of these attacks. And then there are untargeted poisoning attack. Untargeted poisoning attack aims to degrade the global model performance irrespective of anything. They don't care about particular class. They just want to degrade the performance. So they are more insidious or dangerous attacks, and generally local model poisoning attacks, because you don't care about the model, right? In targeted poisoning attack, you have to care about the model. You cannot perturb the model as a whole. You have to keep it intact. It just need to misclassify a particular level rather than all levels. But in untargeted poisoning attack, you don't care about all, so you can just perturb the model. That's why it can also be called as model poisoning attack. And in targeted poisoning attack, you mostly are tweaking the data. You just want to get one set of data to be misclassified, so we can tell it data poisoning attack too. One example you can see here, like already discussed about label poisoning attack. Like attacker wants to change level 8 to 3, 9 to 1. So when the aggregator tests that model, the aggregator will feel that okay, it's working good for 2. It will not test for each particular classes, right? It will check the overall accuracy, and the overall accuracy was not impacted much. So it will be treated as an honest model, and it will be aggregated. So that's why this attack is like very dangerous, like hard to detect attack, level flipping attack. And it has been observed, obviously it's intuitive, by the way. Number of poisoned samples, if you'll increase it, then it will increase the attack success rate, and if you'll increase the attacker, it will also increase the attack success rate. Okay, just give me a second. Just jumping to backdoor attack first. In backdoor attack, we visualize like adding some patch or adding some trigger to a particular image, or adding some malformed text in a text. If you see that there are some text written, and we can put some two dots. If you see some variety of in some different regions, people put some different characters. I don't know what they are exactly called. So, and they have the same meaning, but the model can get confused by them. So in backdoor attack, the data is perturbed and manipulated by adding something extra, like some trigger. So these are basically classified as semantic backdoor attack, Trojan backdoor attack, and dynamic backdoor attack. In semantic backdoor attack, nothing is added. The input features are not added, but you want, the attacker doesn't want all cars to be classified as birds, but the attacker wants only the cars painted in green or the car with a racing stripe to be misclassified as a bird. So this is called semantic backdoor attack. In Trojan backdoor attack, you want a simple 9 to be classified as 9, but if you put a small dot somewhere in 9 which is not recognized, like you are not noticing, you are as a user you are not giving a notice to that particular patch or that particular Trojan, but due to the presence of that particular Trojan, that model will be misclassified to what attacker aims it to be. Like the 9 can be misclassified to 1. That's how the attacker has trained the model. The attacker trained the model 9 with 9 and 9 with a Trojan as 1. So while learning the model, how model learns? So model try to find the distinguishing features between the samples. So model find that, okay, this particular dot or patch is very influential because only due to this 9 is getting classified as 1. So that patch has very high importance. That patch gets very high importance in the model training, and that leads to an attack. That is Trojan backdoor attack. And but there are two different studies going on, right? Attack and defense. So the people who are proposing defense are smart, and they are proposing some measures, be it statistical measures or whatever, to detect that, oh no, this model is malicious because this model has got some is giving importance on something weird at a different place, like in corner where it was not supposed to be. So now there is a need of dynamic patching, like dynamic triggers, and that's how people use GAN, people use encoder decoder. There are a variety of techniques that can be used to uh, generate dynamic patches. I will discuss one of my means we propose this attack, local model poisoning attack. This is untargeted data poisoning attack, and these are, when we propose attack, like it's not simple to propose an attack, because when you are proposing the attack, that should fool the defense. We are not, when we propose attack, we don't talk about simple aggregation that we discussed in the federated learning setting, that you are sending the model and the server is blindly aggregating it. No, the server is trying to find the outliers. So it's not simple to propose an local model poisoning attack. You cannot send anything and tell that, oh, this is a model, you accept it. The server will not accept it. So you have to carefully craft that model. You have to carefully craft that model and send to the server such that the server accepts it for aggregation, and the global model performance is degraded. So that's why nowadays local model poisoning attack are a more subject of a study, and people are trying to propose model poisoning attacks which could fool the smart defenses. You can just visualize this. The second point, a malicious model can be expressed as a function of honest model. Just visualize, because you don't want to send something anything. You want to send something which looks meaningful to the server but is not actually meaningful. So you start thinking to change something in the benign model such that it becomes useless and it gets accepted. So the what existing attacks do, that they add something like the delta m equals to delta wb. When I wb, I am telling honest, benign means honest. So delta m equals to delta wb plus gamma y delta p. P is some perturbation and gamma is some scaling. So they are adding some perturbation and doing some scaling and running some optimization function to find that perfect delta m that would be good to fool the server. But it's very costly. It's very, you have to solve that optimization problem, you have to apply multiple constraints and all, and it becomes based on our study, we claim that it becomes computationally infeasible to search for such a solution. So, so what we propose is that we propose a deterministic attack as where the function we update the delta m as delta b delta cl. Delta b is the benign update and delta cl is the compromised leader update. So I will show it with this diagram. So in step 1, as we know, the server disseminates the model to all the participants. Just imagine that 2 of the participants are malicious. But in the step 2, everybody is training honestly. Everybody, all the 5 participants trained honest models because they have data, they have good data, right? So they trained honest models. In a step 3, I will tell you a property of cosine similarity which I use to frame this attack. So for given 2 vectors A and B, for given 2 vectors A and B, if this is the cosine similarity between them, there exist many such vectors which will have same cosine similarity as these 2 vectors have. I will repeat it. For given 2 vectors A and B, there exist multiple vectors C such that cosine similarity between A and B is same as cosine similarity between A and C. And why we utilized this concept to frame this attack? Because the defense are many defenses are based on Euclidean and cosine similarity measures. They try to find the outliers in terms of magnitude and direction. So Euclidean is like about restricting the magnitude and cosine is about looking at the direction. So they find the outliers in terms of cosine similarity and magnitude in terms of Euclidean distance. So we utilized a property of cosine similarity based on what we could generate a local model which looks exactly cosine similar to the honest update, but it is totally in other direction. It is totally useless. And then those 3 participants, the honest participants sent the honest updates to the server, while these malicious participants changed the perturbed updates to the server. And you can see that they are adding some epsilons there, epsilon 4, epsilon 5. Why? Because there is another kind of a concept, Sybil attack. So if the server will get the exactly same model from everybody, the server will think, oh, something looks fishy. It looks like many of the other participants are compromised and they are sending the same update back. So you need to add something more to that malicious update which keeps you little different from uh, all the malicious participants to fool the server, and the server aggregates all of them. And we have shown it with an example, like you see in the last box, an example in 3D plane for given vectors B and C. Vector B is 2 2 1 and vector C is 2 1 2, and the server is thinking that, oh, I'm sure that these 2 vectors are honest. So the cosine similarity between B and C is 0.89. What server is trying to find? Server find a malicious vector 3 2 1, and you can see M is exactly M is has cosine similarity almost 0.97 to B. Like 2 to 1 and 3 to 1 has very high cosine similarity. At the same time, M has also same cosine similarity with C, that is 0.89. So M will be selected by the server. And this is how we frame this attack. This was the intuition behind this attack. I think I will stop here and I will leave the I could have loved to cover the defenses, but I will just give a brief idea that the defenses to mitigate such poisoning attack and inference attack are based on both statistical and cryptographic measures. There are these are what I've written are few among them which are used to frame such defenses. Yeah. And now I would like to take some questions. I can share these slides. I would find share these slides and That's fine.
Yeah, first of all, I thank Dr. Ash Kashyap for providing his time and valuable insights in federated learning. And thank you so much, Dr. Kashyap.
Thank you very much, sir.
And if you can provide the recording of the video,
Sure, I will.
yeah, you can send it to me. I will share it with the department
Yeah,
and all the slides as well. And if there is, if any of them wants to collaborate with you in future or anything they would like to ask, I will provide. You have provided already the email ID. I
yeah.
think the students can, if they have anything, they
Sure.
can get in touch
I'd
with you.
love to. Yeah, yeah.
And I'll hand it over to